Okay, so here we are with yet another question. Three charges of magnitude plus q are arranged at the corners of an equilateral triangle. Find the charge needed at the center for the arrangement to be in equilibrium. Now, when we are discussing equilibrium here, that does not mean that this charge should be in equilibrium, this charge should be equilibrium, or this or this. But what we are trying to say is that the entire system, all charges are in equilibrium. The net force on any of those charges is zero. So let's consider two possible cases. Let's say that q dash is positive. Now if q dash is positive, it will experience a push force from this charge downwards. Let me draw this in the diagram itself. And again push force from this charge from like that, from this charge, and another push force from this charge, showing it in the diagram like this. And the thing about these push forces is that they are all equal in magnitude because distances are same, charges are same, the angles are 120 degrees, 120 degrees. And in that case, since all forces are equal in magnitude, the net force will be equals to 0. Now what if q dash is negative? If q dash is negative, then the forces on q dash will change. How will they change? Let's see. Due to this charge, it will be a pull force. So pull force, again pull force due to all other charges, and again all those forces are making 120 degrees with each other, and hence net force will be equals to 0. So it does not matter what q dash is. Q dash may be positive or negative, but it will always be in equilibrium. Now we are not interested only in the equilibrium of q dash, we are also interested in the equilibrium of the charges that are at the corners of these triangles, so of this triangle. So all the three charges, they must also be in equilibrium. So let's change page and see what we can do about it. So I have a triangle and I'm drawing this a crude triangle, and I have three charges here. The q dash is here. Let us name the triangle A, B and C. Now what about the charge at A? Charge at A. Now again there are two cases. Case 1, q dash is positive. If it is positive, it will apply a push force, and the other two charges will also apply a push force. And as you might see here, this becomes very interesting to note. Since these angles are equal, the resultant force will be upwards. How do I draw this? Okay, the resultant force, let me draw it this way. The resultant force will be upwards, and hence no equilibrium. No equilibrium. This is the term for equation. No equilibrium. Hence no equilibrium. Now we talk about case 2. Q dash is negative. Now if Q dash is negative, again considering the charge at A, it will apply pull force because Q dash is negative, whereas the charges at B, and C will apply push force like this along the lines. So pull force by Q dash and push force by B and C. Now, is this possible to keep this in equilibrium? Or if this is an equilibrium, what is the value of Q dash? So let's mark all these forces first. This is force due to Q dash. This is force due to B, and this is force due to C. Now, what will be force due to Q dash? Now, we all know that the distance between the vertex and the centroid is a by root 3. That is something that you have to remember, keep in mind. So the force is going to be, this force is going to be F is equals to K Q dash small q upon A squared divided by 3. So 3 goes up. And what will be the force due to B? That will be equals to F equals to K Q squared, because both these charges are equal, Q and Q, Q squared upon A squared. The force due to C here, this force will be same, F is equals to KQ squared upon A squared. Again, changing the page. So we have KQ squared upon A squared, KQ squared upon A squared, and 3KQQ upon A squared. And since it was an equilateral triangle, we must remember the angle was 60 degrees. So these two half angles will be 30 degrees or 30 degrees, or you can simply write it as 60 degrees. So first we are going to find out the resultant of these two forces. How do you find out the resultant? You simply apply parallelogram, and if the forces are equal, you will get F squared plus 2F squared cos 60, that is half, and that will be simply equals to F root 3. So the force in this direction of the resultant of the two charges at B and C will be equals to root 3 KQ squared upon A squared, and that force must equate this force for equilibrium to happen. So 3KQQ upon A squared. Now when we are going to solve this, we'll see one K is out, one small q is out, A squared is out. So what is the value of capital Q that you are going to get? The capital Q will be equals to Q upon root 3, and it will be negative.